Okay, good morning, everybody. Today we are going to talk about greedy algorithms. Before we talk about greedy algorithms, if you haven't done so already, please enter the Top Hat code to record your attendance, number 0093. Again, that's 0093. So we are going to talk about greedy algorithms. What are greedy algorithms? Well, greedy algorithms are algorithms that exhibit the greedy strategy, which means we do what looks good now, and we don't think about the greater implications, the bigger picture. All right. In more technical terms, we do what is locally optimal with less regard for what is globally optimal. Now, if the greedy algorithm is going to be successful, then what is locally optimal should also be globally optimal. So that's part of our discussion today, is which algorithms does a greedy strategy work, when does it not? And the interesting thing is sometimes it works for some data sets for a problem, and it doesn't work for other data sets for problems. So that's also something we need to discuss. All right. So here's our overview. We're going to talk about what an optimization problem is. What is a greedy strategy? We sort of touched on that already. We're going to review or discuss some greedy algorithms. And then we are going to also mention at the end some greedy algorithms that will arise in our course later on. So we are not done with greedy algorithms, but this is our only lecture about greedy algorithms. The other greedy algorithms will appear here and there, just like we have a lot of randomized algorithms. So we have electron randomized algorithms, but randomized algorithms also arise here and there in different contexts. All right, so what is an optimization problem? An optimization problem is a problem in which we have an objective function. Objective function could be something that's complicated, or it could be something that's simple. For example, the sum of two numbers could be an objective function, and we want to figure out which two numbers should we add to each other to give us the greatest sum. So if we have an array, right, of n numbers, which two should we add to do that? So that's called an optimization problem. Now we have two main varieties of optimization problems. One of them is called a minimization problem, and the other is called a maximization problem. And guess what? What do you need to do in a minimization problem? You need to minimize the objective function. And in a maximization problem, what do you need to do? You need to maximize the objective function. Okay, so that's very easy to talk about. Obviously, the challenge is when we're actually coding this stuff. So what is the greedy strategy? As we sort of mentioned already, we do what is locally optimal, which means what looks good right here and now. And we hope that it's globally optimal, that it provides the best possible overall solution. So I have a question for you, which is, if the locally optimal is the globally optimal, then it's obvious why we would want to do that. But why would we consider the locally optimal if it doesn't necessarily guarantee us that? So here's the thing. Finding what is locally optimal is usually pretty easy, or at least relatively easy, right? Figuring out what is globally optimal by looking at all the possibilities, that might be 2 to the n, it might be n factorial, it might be n to the n, right? So thinking about what's globally optimal is often very expensive. So if we can do what is locally optimal, and it turns out to be globally optimal, that's great. But we understand why it's not always so simple, or even a possibility to do, to just focus on what is globally optimal directly. Okay, so we're going to start with a very simple problem. And the problem is this. We have an array of numbers, and we want to figure out what permutation of the array will maximize this. Okay, maybe should I have an example? Okay, well, let's put an example here, okay? So let's do this. All right. Okay, so let's take an example. So our array is equal to 4, 6. Okay, so what are my choices? So I could do choice one. This is obviously a very simple example. Choice one is to take, I can do 0 times 4 plus 1 times 6, which is how much? Does that come out to? That's just 6. Or I can do choice 2, right, where I flip them around, right? I reorder the array. So I take 4. Okay, so let me just be more clear. So I use my array as is, right? And choice 2, I permute the array. So I say use the array like this. And now I'm going to get 0 times, what that? 0 times 6 plus 1 times 4, and that's only equal to 4. So obviously choice 1 is better. Okay. Okay, so anyone have any suggestions about how to do this?
And it just sorted the array from the small
Okay,
one.
that's right. Okay, so one option would be to check all permutations, right? I take each permutation and then I multiply that. Okay, so we call that brute force. That's a brute force approach. Okay, so there are n factorial permutations now. When n is 2, it's not a big deal, right? In fact, that would be the right way to do it, is just to check both possible orderings, right? Once we have our n factorial permutations, or as we get our permutations, we compute the sum, right? We call that a dot, it's not really a dot product, it's sort of like a dot product, right? And then we compare that sum with whatever our max is so far, and we eventually return the max. So we have what? We have O of n to compute the sum times n factorial possibilities, and that makes O of n plus 1 factorial, right? So that's pretty bad, right? Even n squared we already know is bad. So who was that? Was that Cheng before?
Yeah, it's me.
That was Cheng. Okay, so Cheng suggested another approach, which is to sort the data. So if we sort the data, in which order do we sort the data?
From small to large.
Small to large, what we call increasing order. So now the largest element will be in the last position. Okay, now we can make it a little bit more interesting. What would happen if, we used, it was absolute value, right? That would be kind of question I could ask on an exam, right? Take a problem from the class and switch it up a little bit. So how would you modify the problem there? But okay, right? So we sort it. Why are we doing that? Because we want the largest number to be in the largest index. Because then when you multiply them, and it's not just about the largest, the second largest being the second largest index. So that way, when we do this dot product over here, right, we'll be weighting the numbers that are highest with the highest number. Okay, so how much time does that take? Well, to add it all up takes O of n, but I need to sort, so that's n log n. But that gets us back to another question, which is a question we talked about a lot in lectures 3 and 4, which is, okay, we have a whole bunch of sorts. What sort should we use? So I'm going to update the slide accordingly. What do you suggest?
Heap sort,
All right. Why did you say that, Omar?
because you can use max heap here.
Well, we could use a max heap, but remember, we're sorting the numbers. We don't need like a repeated max. So you're right, max heap sort is good because it's n log n. Are there any other options that might be better though? Is n log n the best we can do for sorting?
Oh, we can do O of n with quick sort.
With which sort?
Actually, heap sort.
No, heap sort doesn't do O of n. No, heap sort is n log n. Which sort can do O of n?
Counting sort.
Counting sort or radix sort. So I'm going to say this. Okay. Use O of n sort if possible. Okay, when is it possible? When can we use the O of n sort? This is going to be important not just for this example, but for other examples today and other examples in the course. So when is it possible? Is that Ming? When can we
When
use it?
the
Yeah, go ahead.
when the data sets are not scattered.
Okay, so where data is confined to a fixed range, let's say, limited precision, right? So not, or let me say this, fixed precision. Okay, so then we could get O of n instead of the, and then instead of the n log n, we get it down to O of n, right? So again, that's important not just for this example, but we have other examples where the sort dominates what we're doing. All right, so here's some code for it, right? Let me just change that syntax there. Okay, so we can do this as you see here, or you could also use list comprehension. Okay, so this allows you to do that whole loop, right? So it takes these 5 lines of code, 4 lines of code, and condenses it into one. So that's one of the nice things about Python, right? Any questions about that example? Examples, I guess, get more difficult as we go on today. All right, next problem is the mouse assignment problem. Okay, what is the mouse assignment problem? We have a bunch of mice. We have a bunch of holes, and each hole gets 1 mouse. All right, does this remind you of something from discrete structures? They don't call it the mice hole problem. What do they call it?
Pigeonhole?
A pigeonhole, right? Except remember, in the pigeonhole, you could have multiple pigeons in one hole, right? If you have more pigeons than you have slots, then you're guaranteed that. And if you have don't have so many pigeons, you could still get more than one. Okay, so in this case, each mouse goes in one hole. But what we're trying to do, here's where the greedy part comes in, is you want to get the mice into the holes in minimum time. So you have to, you want to figure out, which mouse is near each hole, okay? And then what we want to know is how long does it take for the mice to get into the holes? Now, the truth is, by the time you run this algorithm, the mice would have all been in the holes anyway. The mice don't need, they don't need a Python program or Java program to help them get into the holes, but theoretically speaking. Okay, so here's our algorithm. We sort the mice, we sort the hole positions, right? So each mouse is, let's say, on an x-axis, and each hole is along the x-axis. And then we define distance by the absolute distance between the mouse and the hole, and we find the maximum distance of those, and that will tell us how long it takes. Does this remind you of anything else we've done in the class? Not exactly, but similar.
The nearest dot.
You call it the closest pairs problem, right? The closest pairs problem in one dimension. Similar, not exactly, but a similar kind of problem. Okay, can someone tell me where is the greedy part here? It doesn't say in the slide, but where is the greedy part here? So we're taking the maximum distance, right? So we look at all the differences between a mouse and the holes, all right? And we take the maximum of those, right? So here is here is some code for that. Okay. Fine. Okay, and now we get to one of the most classic examples of a greedy algorithm. All right, I imagine that all of you have taken CS 220. And what book did you use for CS 220? Anyone use a book?
God, it's a Zine book.
Use a Xi book? With me or with someone else?
Else.
Someone else uses Xi book, really, for discrete math? Okay, so there was also the Rosen, that big fat book that's like over 1,000 pages. Rosen discrete math and applications. Right, so this example is there, but it's a classic example. So how do you make change? Right, so let me give you an analogy. All right, so you go, not an analogy, a real life example. So you go to the store and you pay, you buy an item for 79 cents. Today, like even an egg, it's expensive. You could pay 79 cents for an egg. My daughter went to a cafeteria and they charge $1.50 for a tea bag. Okay, so let's say you buy an egg for 79 cents and you pay with $1. Those of you who are still using cash and not all kinds of electronic payments, cryptocurrencies and so on. Okay, so what change should you get? So if the cashier gives you 21 pennies back, you will probably not be so happy. The cashier is supposed to use a algorithm, whether they know the word or not, to figure out the smallest number of coins to give you change, right? So they shouldn't be giving you 21 pennies. What should they do? I'm sorry, I said the example backwards though. So let's go back to the example here, right? So the item costs 21 cents. I'm not sure what you can buy for 21 cents anymore. So you actually, the change is 79 cents. So you don't really want to give the person 79 pennies as change. So let's look at, these are some of the options. These are not the only options, but those are some of the options, right? Which one of those is going to be the smallest?
The last one.
The last one. Can we do better than that?
Yeah.
What could we do that would be even better than the last one?
I think 3/4 and 4 pennies.
Right, so 3/4 and 4 pennies. So 3/4 and 4 pennies is 7 coins compared to, we had 12 down here and 55 and 79 and 31, right? So that's Young Ying, we changed the problem here, right? So the item costs 21 cents, so you're giving 79 cents change. Okay, so how do we do this? How do we determine what the right number? And cashiers do this all the time. Cashiers who haven't necessarily gone to college and who knows when they last took mathematics. They do it and they're pretty good at giving the right change. So keep in mind that the even if the machine tells them how much change to give, it usually doesn't tell them which coins to use or which dollar bills to use, right? They figured that out. So, one way to do this would be to try all possibilities, right? You look at all the different possibilities of the different coins that are there, and that's going to be exponential time. So we really don't want to do that, okay? We call that exhaustive search or brute force. Not really a good idea. It won't finish. Okay, so we take a greedy approach. And the greedy approach says, take the biggest denomination of coins and try that. And then when we exhaust that, we move on to the next lowest denomination of coins. Okay, so we're going to do that. So we say, how many dollar coins can we use? 0. We look at the remainder, we have 79 cents. Then we take the number of half-dollar coins. We say, how many half-dollar coins? Yeah, well, that works. So if you have half-dollar coins, use 1 half-dollar coin, and you have a remainder of 29 cents. Then we say, how many quarters do I need for 29 cents? Well, I need 1 quarter, and that leaves a remainder of 4 cents. And then I try the other things, right? So I tried the 10 cents, but that doesn't work. I try the 5 cents, but that doesn't work. And I try the 1 cent, and that does work, and it's 4. So Qi Dong is saying, looks like dynamic programming problem. this is, it sets the stage for dynamic programming, but it's not really dynamic programming because dynamic programming is not greedy. Okay, dynamic programming is not a greedy strategy. So you're right. You could use dynamic programming for this, but dynamic programming does not use a greedy strategy. Okay, so in the end, assuming we have half dollars, we use $1/2, 1/4, 4 pennies for a total of 6 coins. All right, so here is, well, before we get to the code for it, does this work? So it turns out, and this is sort of interesting, and you got to wonder if our, the founding fathers of the United States of America, or ever made the mint, whether they were thinking about this or not. Keep in mind, I think there used to be other kinds of coins, right? Were there 2-cent coins in the United States, 3-cent coins in the United States? Very possible. Anyone here collect American coins? No? Okay. So what would happen if the United States had a 39-cent coin? It also had, in other words, it had a 50-cent coin, it had a quarter, it had a dime, a nickel, and a penny. It also had, for whatever reason, a 39-cent coin. So what would our algorithm do? Our algorithm would try the 50-cent coin, it would work. That would leave us with 29 cents. We would then skip the 39-cent coin because it's too big, do the quarter, and then we're left with 4 pennies. So once again, we'd have 6 coins. But if I were able to use the 39-cent coin, then how much would I need? Can you write in the chat? How many coins would I need? Well, I wouldn't just need 1 penny. I need 1 penny and Rabina, I would need 1 penny and what else? A penny and 2 39-cent coins, right? So for a total of 3 coins. All right. So the greediest strategy would not work. All right. So what I want you to understand here is the greediest strategy works for some denominations of coins. It doesn't work for other denominations of coins. So you have to not just understand the problem, but you also have to understand the data, the input data for the problem to figure out whether a greedy strategy is going to work. All right. So here is some code for the making change problem. All right, we're going to pick this code apart. All right, so this code is not perfect. First, let's explain the code, then let's figure out what we could do better. All right, so first of all, let's understand the inputs. Okay, we have 3 inputs. Okay. The first input is the coins. Okay, the list of different coins in decreasing order. Okay, so that's part of the greedy strategy, is to make sure it's set up in that order. All right, we have M, which is the number of different coins. Okay, so we have 1, 2, 3, 4, 5, 6 in this array. And then we have V. V is the value for which we're trying to make change. Okay, so in our example, V is 79. Okay, so we check. Okay, if V is 0, I return 0. Why am I returning 0? Because I can't make any change. I don't need any coins for 0. All right, now I'm saying, okay, how many coins do I need? I need, basically, I start with a very large number and I'm going to change that pretty quickly. All right, so what I do is I try the different kinds of coins. So first I try coin type 100, right? There's number 0, position 0, which is 100. And I see if that number is less than V, then I reduce the value for which I need to make change, and I call this function recursively. Okay, so you see what I'm doing. So what's going to happen is that, well, 100 doesn't work. So then I'm going to try it with 50, right? And I'm going to say, okay, it's 79 minus 50 gives me what? I'm going to call min coins with what? 29, right? Because I'm going to take the 79 minus the 50, and that's going to give me 29. Okay, so I call that again, and then this is just where I update my final results. Okay, so don't worry too much about this. It's sort of a technicality there. All right. Does anyone see some sort of problem with this algorithm? It's not wrong, but it's not great either. there anything that we could do a little faster? Here's what we could do faster. See, we're going down one coin. What is memo? Right, we're going down one coin at a time. So for example, when we get to the end and we have 4 coins left, we're going to take that 4 cents minus a penny. And we're going to call it recursively, and we're going to take 3 cents minus a penny. We're going to call it recursively, and we're going to say 2 cents minus a penny. We're going to call it recursively, and we're going to do 1 cent minus a penny. So we could speed this up by figuring out using the modular arithmetic or division, how many coins we need of a particular type, right? So here you can see the trace of this algorithm, right? So this just seems a little wasteful to have to do it one at a time. We could figure out pretty easily that you just need 4 pennies and be done with it at that point. Okay, so that's not so good. All right, so let's analyze this greedy algorithm. So we had a loop. Okay, we have a loop over m, but how many times could we call this? In total, we could call this v times, right? Because v gets reduced. Sometimes it gets reduced by nothing. Sometimes it gets reduced by 1. So the amount of time it could potentially get reduced is the number of different coins that we have to attempt times the value itself, the number of pennies. Okay, so if we use that algorithm, and I took that from Geeks for Geeks, okay, so Geeks for Geeks is a great site, but don't accept everything you see there as the best possible approach. There are bugs, and there are also design flaws. So this is not a bug, but it's a design flaw, right? So it could take O of m times v. Okay, if we have some large denomination coins, so we had a 50-cent coin, then it'll cut out, some of that time pretty quickly. All right. However, as I mentioned before, if we use division, right? So if I take 4 and I divide it by a penny, I know I need 4 pennies. I don't have to do that 4 times to go through that. I just do it 1 time. So we'll get our time down to O of m because we only have to iterate over the denominations of the coins and not, each value 1 by 1 for each of the coins. Okay, so again, if you take the code as is, it could be as bad worst case of m times v. If we make that minor improvement, right, we can get that down to O of m. Okay, our next example is something called Egyptian fractions. Has anyone heard of Egyptian fractions before? Maybe you've seen them in a discrete class or somewhere else. Anyone see Egyptian fractions before? So we're hanging out in the Middle East here, right? We had a Babylonian method for square roots the other day. Today we have Egyptian fractions. That was the cradle of civilization back in the day. Okay, so Egyptian fractions were a sort of a limited view of fractions. It said we understand that there are things fractions, right? We don't just have whole numbers, but fractions are always of the form 1 over something. 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. Those are the fractions that we had. So the question is, how do I convert a number like 4/7 into a bunch of fractions? Okay, a bunch of Egyptian fractions, or what we call unit fractions, right? So how do you do that? Well, you can try all different possibilities, but we want to be something a little bit more systematic, a little bit faster. Okay, so here's the rule of thumb. Again, it's a greedy strategy. So everything we're doing today is being greedy, right? We're going to try 1 over x before 1 over y. What does that mean? For the smaller the x, we try that first. So we're going to try 1 over 2 before we try a 1 over 3. Okay, so that's the example, and here's our code. Okay, so let's just walk through the code here. So we have a numerator and a denominator. All right, and what we do is we compute these things. And the next slide, you'll see an example, so it'll be a little bit easier to understand. So we're computing the DR over the NR. Okay, so we're basically flipping the fraction. Okay, we're multiplying it by X. We're taking that X, multiplying it by the numerator, subtracting off the denominator, and that will be our new numerator, and this is our denominator, and then we add these units together. Okay, so again, you need an example to understand this. All right, so let's take a look at this picture here. All right. Sorry, let's just make that smaller. No. Okay. All right. So what is our original fraction? Can anyone tell by looking at this picture? Let me bring the chat back. Can anyone tell by looking at the picture what is the original fraction we're starting with?
7/15.
7/50. Okay, so we compute the new and well, we compute X. Okay, so we compute X, and that becomes part of our result. Okay, then we compute the new NR. So the new NR is X, which is 3, times 7, which is 21, minus DR. The old DR was 15. That gives us 6. Okay, and we compute the new DR. The new DR is the old DR, which is 15 times 3 is 45. And then we get the X. So the X is the ceiling of the DR over the NR. So the 45/6, the ceiling of that is 8. And so our next unit fraction is going to be 1/8. So we have 1/3 plus 1/8. And then we do the next one, right? So we take our X, which is 8, multiply it by 6 is 48, minus the 45 is 3. And we take the new DR is the old DR times the X. So 8 times 45 is 360. And then the X is the ratio, it's 120. So you get 1/20. Okay, so 7/15 is equal to 1/3 plus 1/8 plus 1/20. All right, that's Egyptian fractions. Okay, now we get to one of the most classic examples of, okay, so we already had the greedy algorithm for making change, but this is probably one of the most classic examples of greedy algorithms that's not so obvious. Okay, so sometimes the greedy algorithm is obvious, sometimes it's not. So this is called the knapsack problem. More specifically, the fractional knapsack problem. So what is that? What is that? Okay, so here is the scenario. A person, a burglar, a robber walks into a house, and the robber has a knapsack, and the robber can put a certain amount of weight into the knapsack. The robber puts more weight into the knapsack than the knapsack has a capacity of, it will rip, and everything will spill out over the floor, and it will be very difficult for the robber to steal the things that he wants to steal. Okay, so what should the robber take? So any suggestions? I'm not going to ask you if you have experience in this, but looking at it from the perspective of the robber, what do you think the robber is going to take? You think the robber is going to take, let's say, a flat screen television, put it in their knapsack?
No.
Why
You should
not?
take small jewelry.
Okay, so then he probably won't do that. He's better off with the jewelry. He finds some cash, right? Why?
Because he can take
Well,
more.
it's not just more value. Okay, there's another piece to this. More value per weight. Okay, that's the key. You look for value per weight. So the value per weight for cash is very high. The value per weight for jewelry is pretty high. The value per weight, the value of a flat screen television may be a lot, but the value per weight of the flat screen television is not a lot. Probably won't even fit in your knapsack. Okay, so that's the general idea, and that's a greedy strategy. It says take the thing that has the biggest value per weight and take as much of that as you can. Then take the next item with the greatest value per weight, as much as you can. And you keep on doing that until you run out of space. Now, The particular version of the knapsack problem we're talking about here is what's known as the fractional knapsack problem. Anyone want to speculate? It has nothing to do with Egyptian fractions, by the way. So this problem is separate from the previous one.
We are allowed to have fractions in this problem.
You can take a fractional item, meaning you could take a fraction of the flat screen television. You could take half of a dollar bill, if that's what fits into your knapsack. You could take half of a necklace and put it into your knapsack, okay? So not all problems work like that, right? If you chop the dollar in half, well, if you get the larger half, then you can actually go to certain banks and they will give you the money for it. If you chop a gold necklace in half, well, it won't be worth as much, but it'll be worth something. If you chop the flat screen television in half, you might as well put it out in the garbage because no one's gonna want to fix it at that point. All right. So not all problems lend themselves to the fractional knapsack modeling. All right. There are other versions of the knapsack problem, in particular something called the 0-1 knapsack problem. Anyone want to guess what that is?
Either you take it or not take it.
Yeah, as we say, take it or leave it. Take it or leave it, right? You can't take half of it. Can't take half of it. Okay, can't take a quarter of it, all right? So it turns out that that problem is an NP-complete problem, okay, which means it cannot be solved deterministically in polynomial time. If you are not familiar yet with NP-complete problems, don't worry about it now. You will need to worry about it later in our course, but today you don't need to worry about it. All right, there is a variation of the 0-1 knapsack problem, which is integer weight capacity, right? Where the knapsack, can hold, let's say up to 10 pounds, not 10.2, not 10.5, not 10.7. It's got to be an integer. And someone mentioned it before on the chat, right? There is a technique called dynamic programming. That's actually our next topic in this course. And we can solve that problem efficiently using dynamic programming, but that's assuming it's an integer weight. If the weight is arbitrary size, then the dynamic programming solution doesn't work. We'll explain why when we do that, but that won't be today, I don't think. Okay, and maybe we'll show up. Maybe I duplicated this slide here and I have it in the other one. All right, so let's look at the fractional knapsack. So the strategy is, the greedy strategy is to sort the items in decreasing order of value per weight. So again, we want the thing with the highest value per weight first, and the thing with the least value per weight last. Okay, so that's the first thing we need to do. We need to sort the data in that order. The second thing we need to do is we iterate through the items and we take as much of this item as possible. Okay, which means two things. Either we take the whole item or we take part of the item. But here's the thing. If we take part of the item, then do I need to worry about any other items? No. You know why? Because this item is more valuable per weight than the next one. So I will take as much of this item as I possibly can, which means I have exhausted any capacity. So I will only move to another item if I've used up everything about all the items that came before it. Okay, so here is code, right? So let's walk through this code, Python code, right? So the first thing is we assume we have these objects, and the objects have a item number, they have the value, and they have the weight. Okay, they have the weight of each item, the value of each item, and we create a list. Okay, and then we are sorting the items. This is we should fix. Okay, so we're sorting them. Let's just be more clear here. Okay, we're not sorting the items by value. We're sorting the items by value per weight. Or you could say it like this, VAL of I divided by WT. That would be a better way to say. Okay, so that's the first thing we do, is we sort them by this ratio. And right, so we're sorting them and we pass in a parameter. Python lets you do this, pass in a parameter. I want sorted in reverse order, right? And then I go through the items. So I keep a running total of how much my value is. I go through the items and I say, right, get me the current weight and figure out how much of it I can take. Okay, and you know what I could do? I'm going to write this a little bit differently. I could say like this. If the capacity, by the way, the compiler, the interpreter will probably do that for you. I could say if the capacity is bigger than or equal to the current weight, then use the whole item, right? Because I have enough room for it. So I'll use the whole item. So that's what this is saying here, right? So my capacity goes down by the weight, right? So for example, if I have 20 pounds left of space in my knapsack, and this item takes 5, so I now will have 15 left. And in the meantime, that value goes up. And I've got another stylistic thing here. So let's just fix this up. So we have curve value and curve value over here and curve value over there. Any others I need to fix? No. Okay, so again, in this loop over all the items, I have 2 choices, right? Choice 1 is if the capacity is big enough to accommodate this item, then I use this item. So my capacity goes down by its weight, my value goes up by its value. Otherwise, I take as much as there's room for. So I say, okay, how much of the item can I take? And I only go up by that percent of the value. So if the item is worth $10, but I can only take 30% of it, then I get $3 more value. And I have a break here. Can someone tell me why I have a break there? So I have a break because if I can only take a fractional part of this item, that means I can't take any more items. That means I've used up my capacity. I always want to take as much of this item and not leave room for the next one in a greedy strategy. All right, so how many operations? Well, I need to create these ratios. They're n items, so that took O of n. And I have a loop here, okay? The loop is also O of n. The question is, how long does sorting take? Remember I told you earlier today, right? We always have to ask the question, how long does sorting take? And which sort am I using? So which sort should I use?
You're using TimSort here.
Which sort?
TimSort?
Okay, so you're right. I mean, if I call sort in Python, I'm using whichever sort Python gives me, which is, I believe, TimSort. But that's not really my question. My question is, which sort should I use? So if I have an option to call, you know, you will coded, right, sorting algorithms, which one should I use?
Counting or arithmetic sort?
Okay, so I should look into one of the O of n sorts, right? Like a counting or arithmetic sort. And when will that work? Well, if they're in a fixed range and the values of the value per weight are fine. Remember, they're divisions. So it's very likely that the divisions will not be nice numbers. I might have many decimal places, right? If I take 10 divided by 3, I now have 3.33333. So radix sort doesn't work so well for that. But if someone told me that my values per weight are all, you know, 2 decimal places and that's it, then I could use a radix sort very well. All right, so keep that in mind. Okay, so we're going to see this over and over again, where we need to sort something, and it's the time for the sort that dominates the whole algorithm, right? So the rest of the algorithm is O of n. So really, it really matters which sort am I using. Okay, that's what we're saying here. O of n plus the time for the sort, plus the time for the sort. All right, so now we have the 0-1 knapsack problem, right? The 0-1 knapsack problem means what? Take it or leave it, okay? We can't take part of an item. And again, that's true in a lot of cases, right? If I take, you know, if I break something in half, it's not worth half of what it was before. It's usually worth a lot less. Can someone give me an example where sometimes the pieces are worth more than the item itself? Jewelry. Okay, so is germ or gem? Gem, right? Okay, is that true with jewelry? So if I take a necklace, let's say a diamond necklace, and I take the diamond out of the necklace, you think the diamond is worth more or less? I don't know jewelry. I don't have a lot of experience. I think it's worth more or less. I don't know. I don't know. Here's an example though. If I sometimes with cars, you know, sometimes the car, if it's an old car, the parts of the car are worth more than the car itself. Right. So if you try to sell the car, you get, maybe you get $500 for it. But if you sell the parts individually, especially if there's a catalytic converter in the car, right? Sell the tires individually if they're good tires, right? So you could get more money. You have to know what you're doing. You have to have a market for it. But that's why the junkyards, they buy these cars. They pay nothing for the car, and they sell the parts individually, and they get a lot of money. Okay. So in the 0-1 knapsack problem, again, you can't take the whole thing. So question is, do we ever have a scenario where greedy algorithm doesn't work? So I give you an example here, right? I say you have 2 items, 3 items actually. One item is 80 pounds and it's worth $80. I pick nice numbers, right? So we take value per weight, $80 divided by 80 pounds is $1 per pound. Okay, then I have other items, and these are 50 pounds each, and they're $49. So that means it's worth 98 cents per pound. Okay, so according to the greedy algorithm, which one should I take? Should I take the one item of, I should take, which one has a higher value per pound?
Yeah.
Which one?
80-pound one.
The first one, right? The first one is $1 a pound. The second one is 98 cents a pound. So the greedy approach would say, take the first one and it's going to be 80 pounds, but then have 20 pounds left of unused space, right? Whereas if I took the 2 items that are 50 pounds, I will use up all my space exactly. I get $49 for one, $49 for the other, $98. I get $98 of value instead of only $80 of value. Okay, so the greedy strategy doesn't work here. Now, had it been fractional, I could have taken this item for $80 and then 20 over 50 of one of these items for another 20 over 50 times $49, which will be about another $20, would get about $100 worth of stuff. Okay, so again, the 0-1 knapsack problem does not necessarily work with the greedy strategy. All right, so this example is called it's called NP complete. We have a lecture on NP completeness towards the end of the semester, one of the last lectures. And we'll look at a bunch of problems like this. And we'll also talk about what do you do when you have problems like this that cannot be solved in a reasonable amount of time. Okay, there is a third scenario. It's really a variation of the second scenario. It's called the 0-1 knapsack problem with integer weight capacity. What does that mean? It means that the capacity of the knapsack is a nice round number. It could be 1, it could be 2, it could be 3, it could be 4, but whatever it is, it's a nice round number. It's an integer. Okay, so how do we do that? And let's take a look at the code here. Well, basically, before we get to the code itself, someone mentioned dynamic programming before, so this is dynamic programming. We will look at it again once we understand dynamic programming. But basically what we do is we iterate over the capacity of the knapsack. We iterate over the capacity of the knapsack. It means we see what happens when the capacity is 0. So obviously we can't do very much. Then we look what happens if the capacity is 1. What can we do? We look at the capacity is 2. What can we do? We look at the capacity is 3. What can we do? And then each time we use what we got previously to help us figure out what we can do now. That is the basic idea of dynamic programming, which we'll talk about a lot in the next lecture. All right. So I want you to look at the code, but again, we'll look at the code another time. Okay. So we have a nested loop. All right. One loop goes over the items. How many items do we have? We have n items. The other loop iterates over the capacity. All right. And what I want you to see over here, and again, we'll talk about this more in detail. It's just we're talking about knapsack problem today. So I want you to see an alternative that is available. And let's just look at the three cases here inside the for loop, right? So this case says that either I don't have an item or I don't have any capacity, right? Weight is the remaining, what capacity have. So if I don't have any capacity, obviously I can't take anything, right? What this is saying is if the weight of this particular item, the item that I'm up to, is less than or equal to my capacity, then there is possibility of using it. So I see which is bigger. And I'm taking a max here. Everyone see that? Which is bigger, what I have already, or adding this item with the reduction? In other words, this is saying what happens if I remove the space that is taken by this particular item? Can I do better, right? Or how much could I do? So let me be more specific. Let's say this item takes 20 pounds of my space. So I say, okay, how good could I do with 20 pounds less with everything else, plus the value of this item? And if that is more than whatever I had before, then I like it. Then it's worthwhile. All right. The third possibility is that whatever this particular item is won't fit in the remaining space. So obviously I can't use it. So I just use whatever I had before. So this is a dynamic programming solution. Again, don't worry about it so much now. We'll talk more about dynamic programming. We'll introduce it with some simpler examples. But again, I wanted you to see this in context, right? So we have three dynamic programming cases. I'm sorry, three knapsack cases. We have the fractional knapsack problem where we use a greedy strategy. We have the 0-1 knapsack problem where greedy strategy doesn't work in general. We have to, it's NP complete, which means you have to do an exhaustive approach. And then we have the 0-1 knapsack problem with integer capacity where we could use a dynamic programming solution. All right, so we have, we're not done with greedy algorithms. We're done with greedy algorithms in these slides, right? So I just want to give you a sneak preview of some other, and let me, yeah. Right, so where else are we going to have greedy algorithms that come to mind? So we have the three lectures, at least three lectures dedicated to graph algorithms, right? One of those lectures will talk about minimum spanning tree problems. Hopefully you know a little bit about that from, let's say, discrete structures. And we will look at two algorithms for minimum spanning tree problems. One is called Prim's algorithm, the other is called Kruskal. The differences between them we'll study at that time. Both use a greedy strategy, okay? Prim uses a greedy strategy by picking the closest vertex. Kruskal uses a greedy strategy by picking the next largest edge, all right? Maybe I'll put that in the slide here, okay? So we could say here, so Prim uses greedy strategy by choosing next closest vertex. And Kruskal uses greedy strategy by choosing next smallest edge. Okay. Then we have Dijkstra's SSSP, our single source shortest path problem. That's also part of our graph algorithms. All right. And it chooses a greedy strategy by choosing lowest distance. Let's say, let's use the word minimum distance to all remaining vertices. Okay. Anyone familiar with Huffman coding? Anyone heard of that before?
Yeah, I've heard of it.
Okay, so choose, so let's say this. We'll say we use greedy strategy to choose next to smallest frequencies among character frequencies. So this next to smallest. Okay, and we do have a lecture on data compression, both in this course as well as 355 for those who are in 355. So someone said they were in my 320. Did we do any of this in 320? Did we do this? I don't think we did this in 320. Yeah, how did, which thing here came up in 320?
The Huffman coding.
Huffman coding in 320?
Yeah,
Really? Okay,
I think for when we built the Turing machine.
we did a Turing machine for Huffman coding. I don't know. Okay, all right, and then we have approximation algorithms. So let me just remind you and tell you what an approximation algorithm is. So as we mentioned before, we have many NP-complete problems which we assume are intractable, right? They can't be solved in a reasonable amount, meaning polynomial time. And so we have different ways of dealing with that, but one of them is called an approximation algorithm, right? We say, I'm willing to accept an answer that is non-optimal. An answer that is non-optimal, okay? So problems like the traveling salesman problem, the bin packing problem, the graph coloring problem, right? Coloring the nodes of the graph with different colors and seeing how many colors I need so that no two adjacent vertices have the same color, right? We use a greedy strategy. It's not going to be perfect, but it will give us, a pretty good answer, right? So that's sort of a sneak preview of, and what do I have here? I have a description of the minimum spanning tree problem, right? So we're trying to minimize connectivity. It's a minimization problem. There's a picture of a minimum spanning tree. All right, so don't worry about minimum spanning trees now. You do need to worry about minimum spanning trees in about 3 lectures from today when we talk about that. Okay, so we have a good 30 to 40 minutes left. What I'd like to do with you now, and we'll need a volunteer, is to help you not do assignment 4, but to do the part that is so the infrastructure that is a little bit different, okay, for this assignment compared to the previous. Okay, so do we have a volunteer? We're gonna need a volunteer to share their screen and to code for us. We're not going to code the whole thing, but I want to get that sort of the main loop here. No one wants some help? So remember, if you volunteer, Rabina. Rabina's volunteering. Okay, Rabina, go ahead, Rabina. So I'm going to enable the screen sharing. All right, so here's my recommendation. I would recommend that you take, let's say, assignment number 3 and copy it into, all right, so you created a new project. So I would actually suggest that you go back, where is your assignment 3, for example? Open your previous project. That would be my suggestion. You don't have to do it that way, but then you have your code nice and handy. Can you open it from inside PyCharm?
Professor, I don't have that assignment in this laptop. I have it in another laptop.
You don't have the assignment? Okay, well, we want to reuse that. That's why I spend so much time doing these assignments with you, is so you have an infrastructure. So do we have someone else who's good to go that could has the previous assignment handy? We have 25 participants. That's about half a class. Okay, it's not so good. I'm sure we'll have like 90% attendance. All right, Cheng. Opening your PC. Where have you been until now? You were even participating in class. iPad, I got it, okay.
Okay, is it working?
Okay, so I see your 355 stuff. Right, so where are your bring up your 323 project. So I want to see assignment 1, 2, 3 on the side. Exactly, okay. So now we see all the stuff we need there. So let's create another folder. I guess you can call it assignment 4 folder.
Stuck right now, so gonna take some time.
All right.
I don't know why PyCharm do this. I thought IDEA is supposed to be fast.
PyCharm is a great editor, but it also is a hog on memory.
Okay, you want me to copy assignment 3? Just
Copy a
over-
comment 3. No, not the, I don't need the PNG in the output now, but move, yeah, that's exactly what I want you to do.
Oops.
Okay. Okay, so it doesn't really matter actually whether you're doing the trees or the hash table for now. Okay, so here's what I want you to do. I want you to go down to the, not the main, but the, your main loop there. I guess it is the main. Okay.
Those are just testing.
Okay, so what we're going to do is we're going to okay, well, instead of algos,
Mhm.
we're going to create, we're going to call it DS for data structures. Or you could call them structures. How about that? So change the name to structure.
Structures. That.
You could call it that for short. Okay, that's fine. And I'm going to set it up as if you were doing the, which one do you think you're more likely to do?
What do you mean by that?
Like, I don't know if did you look at the assignment yet or not?
Not yet.
No.
So.
Okay, so there are two options, okay? You can either do 4 different hash tables and they give you the, specifically what those are, or 4 different trees.
Oh, I would prefer hash table, I guess.
I think hash tables, okay, so let's actually give them names. Okay, so we're going to, why don't you create variables on the top?
Variable.
No, so on the tippy, all right, for now, you could just do it right here, okay? So we're going to create 4 variables.
Mhm.
Okay. We'll call it hash chaining. And for now, you could set them equal to none. None is with a capital N. Yeah. And then you're going to do that. Going to say hash quadratic. Okay, and we're going to have hash double. And hash cuckoo.
Cuckoo.
Like that, yeah. Okay, so we're also going to need data. All right, so let's look at the assignment and see what the data look like. Okay, so the data is the same kind of data for both, whether you're doing trees or hashing. So can you bring up the assignment?
Yeah, I'm looking at it right
I don't
now.
know if we can see, we might not be able to see your whole screen.
Okay.
You might need to unshare and reshare. You can close whatever you need to close. Okay, good. Okay, so go down. Where's the data part of that?
My code. Data part.
Okay, go down. Go down. Okay. All right, so the trials sizes are going to be 100. So line 113, you already have the sizes there. You could change that to 100. In line 113, change that to 100. Okay, for it goes 1 to 11. Fine. Okay, and okay, and we want to get random numbers between 1 and 100,000. Okay, so I'm going to give you a new way to get random numbers. All right. So keep the old function.
Old function is, wait, I think we use, yeah, it's in the pre.
Oh, we don't have it anymore.
Yeah, we
All
have.
right, we could write it from scratch. Okay, but here's what we're going to do to see, as some of you discovered, getting uniqueness is difficult. Okay, and it slows it down. Okay, so we're going to make a new way of getting we'll call it pseudo random. Okay, so instead of random, we're going to call it pseudo random numbers.
How do you spell pseudo again?
Pseudo,
S
P-S-E-U.
U D O.
GO, pseudo random list. Okay. And I guess we're gonna need a okay. And we need a count. So we'll just say N, parameter N. Okay, so we'll make a list. We'll call it L for list equals an empty list.
But sometimes for Python, you use L, it will give you a warning.
Yeah, because something else is using L. Okay, so we could say result, RES.
RES. Okay.
Yeah, it's an empty list. So this is
This is this, right?
now brackets. Okay, and this will force the numbers to be unique, and then we're going to shuffle them. Okay, so this is a different approach than what we did. Not telling you it's a perfect approach, but it will be a much faster approach. So we're going to do this. We're going to say for I in range n, okay, we're going to say RES dot append. Oh, let's give RES a one number to begin. I don't know. I guess that's biasing it, but we'll do it anyway. Let's put in a 0. Yeah. Okay. So we're going to do this, and if you could change it to 1 comma in line 20
Yes.
instead of
comma.
1 comma n, right?
Okay.
Okay, good. And we're going to append. Listen, watch this. We're going to say RES of I minus 1.
-1, you said?
No, RES of I minus 1.
Oh,
Well, no, bracket. When I say of, I mean bracket, right?
okay.
Bracket. Bracket means square bracket.
Bracket -1.
I minus 1. We're going to take the previous number plus random dot plus random dot rand int between 1 and 10. Okay, so let me explain to you the strategy here. The strategy is that we take the previous number and we add a number between 1 and 10. Okay, why are we doing that? Because that guarantees no duplicates. Okay, because I don't know, again, some of you actually, did this, discovered this, that when you're making these big arrays, making sure that it's duplicate is actually very slow. And then we can return RES. Okay. Fine. You can get rid of the random matrix function. And you can get rid of the all ones matrix function. And the print matrix. Yeah. And we don't need native mults.
Mode, simple mode.
Okay, you can get rid of the simple mults. You can get rid of the matrix split. Get rid of the Strassen. So the part we really need is we need the plotting and we need the main. That's what we really need from last time. Okay, so what we're going to do now is we need to iterate over the 4, actually, let's create 4 functions. Okay, we're going to call, yeah, so they're all going to pass for now. Okay, so we're going to call it build hash Or if you want, it's probably more natural if you do it the other way. Say build chaining hash. And pass in a list. Okay, so what do you want to call it? Data? Data's good. Actually, let's do that. In line 20, instead of res, let's change it to data and change it in the ones below. Okay, good. All right, so we're going to pass for now. And let's make the 4 more.
Okay.
Right, so these 4 functions are going to build the data structure. Okay, so we're not searching for anything yet. Good. And now let's fine. Okay, so let's change the name though. So the second one is going to be called quadratic hash. And the third one's going to be called double hash. And the fourth one's going to be called cuckoo hash. Okay, so now in your code, go down to your code. When I say code, I mean the main. You're going to iterate over, let's figure out where the right thing is. Okay, so I guess it's going to be in the trials part. So go after line 73.
73, okay.
Okay, and after that line 73, you're going to need to get your data. So you're going to call data equals after line 73. You're going to say data equals pseudo random list, and you're going to pass in the size. So what are we calling size here? Size of variable? Yes.
Yeah.
Okay, and now you're going to say for struct. Oh,
Struct. You mean
oh,
right
hold
here?
on. You know what? Let's create a well, I guess we'll create a list of structures.
Here.
Okay.
30.
So I guess we're going to do it down here, where you were.
Right here.
No, right where you were, after line 74. So you could say struct is a here's what you can do. Okay, so in create a new loop right there. You could say for I in we might change it, but for I in range 4. Or better yet, for I in range len structs. Okay, so it's going to iterate over the data structures, and you're going to say struct of I.
What was that again? Wait, but I thought we're doing the iteration for
okay.
structs here.
Oh, you have that already? Okay, so, but no, that's to initialize it. That's to initialize it. Okay, see, here's what we're going to do. All right, we need to build the data structures. Okay, so let's create a list. You could do it on the top. Okay, so in line 66, okay, we're going to call it, we'll call it in line 66 instead of structs, we'll call it build functions. Build functions. Okay, and put the name of your 4 functions in there.
Okay.
without the parentheses, right? Because we're going to iterate over that.
What?
Okay, good. So after we get the data in line 75, go back to line 75. So we're going to say for func in, or better, we could do for I in. Let's do that. For I in range len of build functions. Okay, struct, or if you want, you could say hash table of I, bracket I, bracket, because we're building a list, right? Equals build functions. Oh no, we want to actually call it. Yeah, so you
Want to
could
do it in
say
a dictionary?
no. So we're going to call the function. Yeah, so you could say build functions of data. Build. I'm sorry. It will be called what? Build functions of I. Parentheses. Now build, you need an I first. So the I is in brackets. Build functions of I in brackets, parentheses, data. Okay, so let me explain to you what we're doing here. We're saying we're going to build a hash table for each of the functions that we have. Okay, so we're iterating over the list of functions that we have, and we're going to pass in the data that we got. Okay, so there are a few problems here because it doesn't know what hash table is. So we can define a, well, you can make, here's what you can do. You can make an empty list. So after line 74, because a hash tables is an empty list. Good, good. And we could go back to this. So in line 76, we'll say for func in build functions, let's get rid of the range and the len. And we could say hash table, actually change hash table to hash tables because it's in line 75. Okay, and then in that line there, you could say hash tables dot append. So instead of assigning, say dot append, get rid of the I. Append the build functions of, actually you could say func of data. Append func data. Okay, so what we're doing here, it's func parentheses data, right? We're calling the function to build it with the data. Okay, so what is hash tables? Hash tables is a list of the data structures. Now we want to time them. Okay, so this is the building part, right? There are two parts. There's the building and the searching. So how do we do that? So we use the same mechanism we used before. You can even use the same variable names, but you need to do that before and after each hash table. So not outside the loop, inside the loop, just like we did before. Good. Start time, you're going to do an end time after that. Good, and you're going to get the net time. Good, and then we're going to put that into our dict. Okay, but we're going to have two dictionaries to keep our results in. Okay, so one if you go back to line 67, we're going to have dict build, and we're going to have another one called dict search. Okay, you understand? So you might as well, so in line, so you're going to need to initialize both of those. But for now, let's go down to line 82. So after line 81, before the loop. And you're going to say dict build of brackets, the name of which I guess is the func, right? It's the func.name. You know what? I think it'll be clearer if you change in line 77, you call it build. For build and build functions in line 77, sorry.
Build
And build functions, and then in the line 79. I think that'll be clearer. And then over there, you're going to say build. And then what did we do before? So you do the same structure at 89. Okay, so that's the building, right? You might need to initialize some stuff that isn't there yet. And now we're going to, we need to get some search data. Okay, so we're going to get the search data. We're going to get a bunch of random numbers in the range, in the expected range. Okay, so go back to the top. And where was that random list? Okay. Okay. So what does it say in the assignment? Are we?
You mean the search part?
Okay, so when we search in section 5. All right, so we're going to get oh, wait, hold on. When we do the pseudo random list, it's very important that we unorder it. So it's right now it's sorted. We don't want to use the sorted data. Okay, so here's a little trick you can do. You could call the shuffle function. So go Google Python shuffle just to see the usage. So shuffle does the opposite of sort. You can write your own shuffle function. We'll actually see that in our course. Let's just see the proper usage. So
Random shuffle.
you know, go up to the top. There's a simpler usage. Okay, so it's going to shuffle it. So you could just say random.shuffle, return random .shuffle data. That's important. Okay. So now go back. Well, so we want to make another list to get the data. Okay. Okay, let's limit ourselves to stuff that's in the list. Okay, so we'll call it get sublist. Okay, and we're going to pass in data. Get random sublist. How's that? Okay, and we also need to know how many items. Okay, so we'll call it size. So pass in a parameter size, pass in a parameter size. Okay, good. And you could say for I in range size. Okay, let's create a list called sublist. So in the line before. And we could probably, you know what, we could probably do this in a one-liner. Okay, so we'll say this. We're going to say sublist equals, go in that brackets, data, bracket. Let's create a variable before this line. We'll call it n equals len of data. That'll be a little shorter. Okay, so in the next line, we'll say data bracket random rand int 0, n minus 1.
In the parameter,
Yeah,
0, what?
n minus 1. So we're getting random numbers here. For I after the parenthesis, after the bracket rather, yeah, for I in range size. Okay, and you can get rid of the loop. Okay, so what this is going to do is it's going to just return, instead of sublist, just return. You just return that thing. No, just instead of the sublist, just say return that thing. And if you want, we could just do instead of the n, we don't even need the n anymore. Just say rand int 0 in that line instead of, yeah, exactly. Okay, so we got a one-liner. Okay, so again, maybe we should put a comment here. So before this, we're going to get a random subset or subset of the items in data. Random subset of size, and better yet, say get random subset of size items from data list. Okay, so that's that. Okay, all right, so just one more thing and then we'll stop. So go back to your main loop. So okay, so we're gonna say for, let's say, for search and searches, or
Here.
so you see where the algo is in line 88. You're going to say for search and search functions.
Just
You could call it search functions to make it similar to what we're doing in line 82.
okay. So
Okay, and what we're going to do is we're going to set the time. So get rid of line 89 for now. Okay, we're going to start the time, and we're going to say for get the data. So before line 88, get your sublist. If you want, you know what, you could even do it in line 80. After line 80, you get your sublist equals get your sublist.
this.
Yeah, but in this case, we're passing in not the whole size. Let's say size divided by 10. So, no, data is the data. Gonna pass in, let's say, 1/10 of the size.
You mean here? Or
You know, it just, the assignment says 100, so just do 100.
right here?
Comma size.
Comma 100.
Oh,
Okay, you could change that later, but what we're saying is get me 100 items, right?
oh, okay.
Okay. So then in the search, you're going to start your search and you're going to say after you start the search, you're going to say for item in sublist, and you're going to call the search on the data structure. I guess you could just call the search function, just say search and pass in the item. And then you're going to end the time. So you're going to do that for each item. You're going to end the time, you get the net time. And then in line 96, you say dict of search. Instead of
So you want the time in the for loop or outside the for loop?
no, I want it outside because we're going to search for 100 items. We want the total time for all the search, just like the build was the time for all the building. Okay, that's right. Gonna call that search.
Don't we need to pass in the actual data also, not just the item, like the list we're searching from?
Wait, you're talking about in line 93?
Yeah.
No, because we're searching in the data structure. So we're assuming that we could pass, okay, we don't need to search the data, but we do need to pass in the data structure. So we could call that hash table. Understand?
Yeah, I'm kind of confused.
Okay. Here, you could do this. Okay, go to line 90 and instead of search, you could say for I in len, search functions. Did we make the search functions yet? We didn't make a list of search functions. So you're going to need to create that. Okay. And then in line, you could say search on the next line. You could say search equals search functions of I. And then you could say, okay, so you're going to create 4 functions like those. You could say search chaining hash. Just use the same syntax. Yeah, just make them. Okay, and now you could say search is equal search function of I, then you could say a table on the next line. Table equals, or struct, either one, equals hash tables of I. And then in line 96, you could call search and you're going to pass in the data structure. So you could say the table and the item. So the table will already have the data to Ellie's point. The table already have the data in it. So we're searching for the item in the table. We find out the time when we're done with all those searches, get the net time, and we put that into our data structure. Okay, so that's what we're going to do for today. Okay, so what you can work on is writing those eight functions. Okay, so everyone's going to do that a little differently, but basically you're taking data and you're building a chaining hash. You're taking the data and you're building a quad hash. So you can get that code from like Geeks for Geeks or somewhere. Does that make sense?
Yeah, I got it. So
Okay,
basically,
so we
the
might
framework is
come back to the structure, but I want people to individually work on those 8 functions there. So 4 functions are building it from a set of data. You're going to pass in the data that we got. And then the other is, finding it, finding an item in that data structure. So you should be able to find that code online. Geeks for Geeks are also.
Okay.
Then we'll work on the data structure. So you can, you can test it outside the loop. So outside the main, you can just, test it. You pass in the data. Does it build the data structure?
Yeah, that's what I did for assignment 3 because
Yeah.
okay.
All right. So if we have time, when one of the lectures, we'll work on the infrastructure, but the individual functions, I think people should be able to work on their own. Okay. All right. Thank you, Cheng.
All right, thank you.
Professor,
Yeah.
what's the attendance code?
I don't know. I gave before. Thank you. Thank you, Sagar.
And Professor, for this assignment, should we make 2 like graphs of the search and the insert?
Should you repeat the question?
We make 2 graphs, one for like the searching and one
Yeah,
for the.
yeah. I think it says that in the
Okay.
in the assignment. So basically, you're going to call plot times twice, pass in different data and maybe different captions. So instead of hard coding the caption and whatever labels are going on there, you might might want to vary it. So you can pass that in to the plot times function.
That sounds good. Thanks, Professor.
Okay.